This conference will now be recorded.
Hello everyone. Last day we have already started group 17 and today we are starting with the oxidation state, and after that we will see what are their oxidation power. Then anomalous behavior of fluorine, that is the first element of this group, and then compounds with hydrogen, oxygen and metals, and there will be related problems also. So here, when we are talking about oxidation state, we know that different types of oxidation states are possible. So as you can see in this table, for fluorine, it is -1 only, because fluorine cannot have positive oxidation state. It is the most electronegative element in the whole periodic table. So positive oxidation state is not possible. Then after fluorine, when we go to chlorine, bromine and iodine, all these different types of oxidation states are possible, starting from -1 up to +7. Minus oxidation, that is negative oxidation state, we can see only when it is forming compound with metals, because when there is a metal halogen bond, metal is more positive, that is less electronegative, so obviously negative charge will be over halogen and positive charge will be over metal. But if it is forming compound with oxygen, now oxygen and halogen, so oxygen, it is more electronegative than X, so now the negative charge will be over oxygen and positive charge will be over halogen. Now in this case there is exception also, and when X is not equal to F, because this is not applicable for F. Why it is so? Because oxygen is less electronegative than fluorine, but oxygen is more electronegative than chlorine, bromine or iodine. So that is why, except fluorine, in all other cases positive oxidation state of halogen is possible in their compounds with oxygen. So when it is -1 oxidation state or +1 oxidation state, we need 1 unpaired electron. So 1 unpaired electron accounts for these two oxidation state. If you are removing this electron completely, it will achieve +1 oxidation state, and if one more electron is coming here, that is a gain of electron, in that case it will be -1 oxidation state. After that, how we can achieve +3 oxidation state? Now to achieve +3 oxidation state, one of these paired electron from np5, it must be transferred to d orbital, otherwise we cannot have 3 unpaired electron. Okay, because in this case you have only 1 unpaired electron, but to have +3 oxidation state we need 3 unpaired electrons. So here we have 3 unpaired electron. Then +5 oxidation state, so we now need 5 unpaired electrons. So this pair also we have to break. Now there are total 5 unpaired electrons, and if we want to achieve +7, now the pair which is present in ns orbital, that should also be broken, and now we are having total 7 unpaired electrons. Okay. So higher oxidation states of these 3 halogen, not fluorine. It is realized mainly when halogens are in combination with small and highly electronegative fluorine and oxygen atoms. The meaning of this line is, for these 3 halogen, chlorine, bromine, iodine, they can have positive oxidation state only with those elements which are more electronegative, then only they can achieve positive oxidation state. And more electronegative element is oxygen and fluorine. Okay, so when these 3 halogen, chlorine, bromine, iodine, they will form compound with oxygen, it will be compounds of oxygen and halogen. But when they will form compound with fluorine, this type of compounds are called interhalogen. That is, 2 different types of halogen are forming the compound. So interhalogen, that is completely different topic that we will discuss later. But remember that positive oxidation state is possible only when the other element is F and O. So here we have examples: interhalogen, oxides, and also oxo acid. So oxo acid of halogens are also possible. They are also they can achieve positive oxidation state. That means higher oxidation state. Now oxidation state +4 and +6. that are not mentioned in this table. Okay. Now this can also occur in oxides and oxo acids of these two halogens. Then fluorine atom, as it has no d orbital because it is from second period. So as there is no d orbitals, expansion of octet is not possible. That means this type of that is pair that we are breaking and we are transferring these to d orbital, this phenomena is not possible in case of fluorine because there is no d. So that is the reason we cannot have the higher oxidation state. And another reason which is most important, that as it is the most electronegative in the whole periodic table, so how it can show positive oxidation state. Okay, so that is why it is only one oxidation state is possible for fluorine, and which is minus. Fine. So is there any doubt in the discussion of oxidation state for halogens? Next we'll see oxidizing power. All halogens, they have strong inclination to accept electrons because they are almost at the right hand side of the periodic table. They are non-metallic in nature. Okay, so they will have a tendency to accept electron, and that is the reason they are very good oxidizing agent. That is, in general, you can say halogens are very good oxidizing agent compared to other groups in the P block. Now, if we compare among the four halogens, HCl, Bri, then fluorine is the most oxidizing agent, and it is so oxidizing that it can oxidize all other halide ions. That means halide ion means it is X minus, where X is equal to Cl Bri. Look at this equation. Here we have taken fluorine and it is reacting with halide. That means X minus. And this X is basically Cl, Br and I. So here fluorine is accepting electron from X minus, itself is converted to F minus, and X minus, that is Cl, Bri, now it is converted to chlorine, bromine or iodine, diatom. Fine. Now the rule is, in each case, a halogen higher in the group can oxidize the ions of the lower down. That means if we write F, Cl, Br, I, halogen higher in the group, that means just choose bromine. So compared to F and Cl, bromine is higher in the group. So it will be able to oxidize chlorine and fluorine, but not iodine. Okay, that a halogen higher in the group can oxidize the ions of the lower. So sorry, let me. I mean to say here, in each case, a halogen higher in the group, it can oxidize the ion of the lower down. Whatever I have said, that is wrong. Actually, it is the reverse. So higher in the group, it can oxidize the ions of the lower down. That means if F is present, it can oxidize Cl minus, Br minus, I minus. Similarly, if you have chosen chlorine, chlorine will be able to accept electron, that is, it can oxidize only bromine and iodine, not fluorine. So look at this equation. When you have chosen chlorine, it can react with X minus and it can accept electron from X minus, itself converted to Cl minus. But remember here, X is only Br and I. It is not F, because F is above chlorine and fluorine is more oxidizing. So it is not possible. And if you have chosen bromine, then only one element is there, which is just below bromine. So it can accept electron from the iodide, but not chlorine, that is Cl minus or F minus. So this is the oxidizing power, that is explanation. Fine. Now as we move down the group, oxidizing power diminishes, because fluorine is the most oxidizing. So as you are moving from fluorine to bromine to iodine, obviously oxidizing power is decreased. Now why it is so, the explanation behind it, if we want to give, for that we have to consider this diagram. And oxidizing power, it is basically related to some other processes also. So this diagram, it is based on Hess's law. So according to this law, suppose you are at state 1, you want to reach at state 4. Now you can reach from 1 to 4 directly, or you have another option. First you are reaching to state number 2, then you are reaching to state number 3 from 2, and then from 3 you are reaching to 4. That means you are not directly moving from 1 to 4. You are moving through 2 and 3. But whatever is your direction of moving, in both cases, that is the delage value that will be same. That means the delage enthalpy change that you are having from when you are moving from 1 to 4, that will be equal to the delage change for 1 to 2, that is delage atom, then delage electron affinity, which is 2 to sorry, it is 1, this is 2, sorry, it is 1 to 2, 2 to 3, and 3 to 4. This is 2, this is 3. Fine. Then 2 to 3 and delage HYD. HYD means hydration. So this is for 3 to 4. So whatever is your direction, whether you are moving from 1 to 4 directly, in that case it is delage. And if you are moving by another route, then it is delage atom for 1 to 2, delage electron affinity 2 to 3, delage hydration 3 to 4. So the summation of all these three, that will be equal to delage, and this is based on Hess's law. Now what we are doing in here, just let me erase all this. Whenever we are saying oxidizing power, it is basically X2 is converted to X minus. But what are the processes occurring here? Watch carefully. First X2, which is a standard state, from X2 by enthalpy of atomization, it is converted to atom. So this is diatomic X2. But you have to break this X2, otherwise individual X, how you can get? So for this process, the enthalpy change is delage atom, that is enthalpy of atomization. After that, when you have reached from 1 to 2, this is 2, your next step will be enthalpy change for electron affinity. Now X in gaseous state, it will accept electron, it will be converted to X minus gaseous. Fine. After that, when you have reached 3, next what you are doing, from gaseous state, now it is in aqueous state. That means enthalpy of hydration we have to consider. Fine. So whenever we are saying oxidizing capacity, basically X2 in standard state, it is converted to aqueous state. But it is not a direct process. All these individual steps we have to consider. That is, first you have to break this from diatomic, now it is monoatomic. Next is you are feeding one electron by enthalpy change is electron affinity, delage EA. Next, what you are doing, from gaseous state you are going to aqueous state, because oxidizing capacity, when we are talking about it, obviously it is occurring in aqueous solution. So X minus, it is not in gaseous state, it is now in aqueous state. So that is why we have written X minus aqueous. Now as delage is a summation of all these three processes, and depending on these individual delage values, delage, that is the overall delage, that will vary. Okay. So suppose in some cases delage atom value is very low, but other two values are high. Maybe in another case electron affinity is very high, other two are low. So each of these enthalpy can vary. That is the three enthalpies. Now if we take the combined effect, first is atomization energy, this is delage atom, then enthalpy EA, then enthalpy hydration. So all these values for these 4 halogen given in kilojoule per mole unit, and this is the overall enthalpy. So plus 79 minus 328, it is electron affinity, so all these values are negative, and this is the overall value. That is, if we add all these three, you will get this value. Now look at the overall delage value. It is most negative in case of fluorine, minus 755. That is the reason fluorine is the most strong oxidizing agent. Okay, than the other three, because this is the overall effect. So when if it is asked that why oxidizing power of fluorine is high, it is basically dependent on all these three factors. Okay, because this factor which is ultimately deciding the oxidation power, it is combination of all these three enthalpy. Next is see, fluorine, as its oxidizing capacity is maximum, it can oxidize water to oxygen. So this is the reaction, fluorine H2O. So in H2O, oxygen is having -2 oxidation state, but now it is 0, and fluorine is having 0 oxidation state here. After reaction, -1. That means it is accepting electron. So it is oxidation for fluorine. Sorry, reduction for fluorine, and fluorine is oxidizing oxide to oxygen molecule. If it is chlorine and bromine, they also react with water, and now the products are different. See, in case of fluorine, reaction with water, what you have obtained? Oxygen and HF. But when it is Cl and Br, now you are getting HX, which is same as HF, but you are getting another acid which is known as hypohalous acid. So if it is chlorine, that is if X is chlorine, it will be HOCl. If F is bromine, it will be HOBr. So we are getting two different types of acid. General name is hydrohalic acid, that is HX, HCl and HBr. And general name for the other acid is hypohalous acid, but the formula is HOX. And what about iodine? The reaction of iodine with water, it is not spontaneous, because what we have seen in this table, as we are moving down, oxidizing power diminishes. So for iodine, oxidizing power is minimum. So that is the reason now reaction of iodine with water, this is not spontaneous. That means iodine cannot oxidize water. On the contrary, what happened? I- can be oxidized by oxygen. That means the reverse reaction is possible. Reverse reaction means, suppose if iodine can oxidize H2O, in that case the reaction will be like this: iodine plus H2O, and it will produce iodine I-. That means iodine accepted electron from oxygen. But this reaction is not possible. It is not spontaneous. That means the reverse reaction is actually spontaneous. And the reverse reaction means now you have HI means H plus is also there. So it is basically hydroiodic acid. So now look at this reaction. 4I- 4H plus. That means it is nothing but HI. So now we have written the reverse reaction. It is reacting with oxygen, and oxygen is gaining electron from iodide, that is I-, and itself now converted to -2 from 0. So this is gain of electron. So now basically I- is acting as reducing agent, and this occurs in acidic medium. So this reaction is the reverse reaction that we have observed in case of fluorine. Okay, so in this way we can explain the oxidizing power. That is, this table is very important. In this table you can see all the individual enthalpy values and also the overall enthalpy values, which is actually the deciding factor for oxidizing power. Okay, is there any doubt? Should I repeat? The first element is fluorine in this group, and as usual it also shows some anomalous behavior that we have already seen. But what are the reasons behind this anomalous behavior of fluorine? The reasons are small size of fluorine because it is from second period. Then high electronegativity. It is the most electronegative element in the whole periodic table, not just in this group. Absence of d orbital. There is no d orbital because it is from second period. And dissociation enthalpy of FF bond is very high. That means if you want to break it, this process will require high amount of energy. So because of these reasons, the difference in behavior that actually occurs, now we will see that most of the reactions of fluorine are exothermic in nature, reason behind it is small size and strong bond formed with other element. So that is why the molecule is very stable. That is a product that is formed when molecule is reacting with other element. That product is very stable. That means the process is exothermic. Energy will be released. It forms only one type of oxoacid, but other halogens can form a different types of a variety of oxoacids. Remember the general formula of oxoacid. If E is the central atom, there will be OH bond present and bond O that is also present. This is the general form of oxoacid. Just for example, H2SO4 is oxoacid of sulfur that we have seen in group 16. So here also, in case of fluorine, you can observe only one type of oxoacid, but for others, variety is possible. HF, that is the compound with hydrogen, that is liquid. Boiling point, see, 293 Kelvin. And the reason is it is having strong hydrogen bonding. But other halides, hydrogen halides, that is HCl, HBr, HI, all are gaseous. Now, if you are thinking that you have seen HCl in liquid form, that is actually the gaseous form that is dissolved in water. But actually, they are gaseous in nature. Only HF is liquid. That means the distance between the molecules are very small. That is why it is in liquid state. That is physical state is liquid. And why they are very close to each other? Because of hydrogen bonding, which is not present in case of the other hydrogen halide, HCl, HBr, H. Fine. So that is why boiling point will be low because their physical state is gaseous. Now we will discuss one problem. Electron gain enthalpy in kilojoule per mole for fluorine, chlorine, bromine, iodine, we have to choose. Now, electron gain enthalpy we have discussed in atomic properties of halogens in last class. Okay, and there we have seen as we are moving down, there is no gradual smooth increase or decrease. Actually, it is maximum for chlorine, but as you are moving down from chlorine to bromine to iodine, or you are moving in the upper side chlorine to fluorine, in both cases it is decreasing. And when I am saying decreasing, it actually means the numerical value. Otherwise, there is always a negative sign because it is exothermic process, energy is released. But when we are saying high, that means you have to focus only on the numerical value. Now, if you look at the options 1, 2, 3, 4, in which option maximum numerical value you can see for chlorine? Can you tell me, please? In which of these 4 options maximum value for electron affinity for chlorine is observed? Because that much information is enough to choose the right option. It is this one, 349. Only in option 3, the value for fluorine, because the value at first it is for F, then Cl, then Br, and then R. So this value is maximum. So without looking at other values, this much information is enough to choose the right option, minus 349. And after that, the next higher value is fluorine, then bromine and iodine. That means maximum is for chlorine, then fluorine, bromine and iodine. Okay, is there any doubt? We have another problem here, which is related to oxidizing power. See, all these reactions are basically oxidation reaction that we have just discussed in the previous slide. But it is asking which reaction is not feasible. Now, what we have seen in this table, just remember, I'm talking about this one. If you are clear about it, you can easily answer this question. Okay, so Ki, that means I minus reacting with bromine, it is converted to Br minus. I am just writing the ions, not the full equation, and iodine. That means I minus given electron towards bromine, and bromine is more oxidizing in nature compared to iodine. That means Br can accept electron from iodine, iodide. but not the reverse one. So this reaction is basically possible. So it is feasible. Okay. Next is this reaction, that is in option B, the reaction that you are seeing, that is just the reverse reaction of the first reaction. In first reaction, Ki bromine, you are getting KBr iodine. Now KBr iodine in the left hand side and Ki bromine on the right hand side. Now if the first reaction is possible, obviously the second reaction is not possible. And we have to find that reaction which is not feasible. So this will be the correct option. But what about the other two? Br minus reacting with chlorine. Now chlorine, which is just above bromine, so chlorine is more oxidizing in nature than bromine, so it can accept electron from bromine, itself will be converted to Cl minus and Br2 will be generated. And the last one, so this is also possible. And the last reaction, this is not halogen, this is that is not halide, this is water. That means whether fluorine can oxidize water or not. But fluorine can oxidize water, that we have seen already. So fluorine is converted to F minus and oxygen here having oxidation state -2. Now it is having oxidation state 0. So this reaction is also feasible. Only the reaction in second option is not possible. So that is why this is the correct option. So is there any doubt in these two problems? Uses of halogen. Fluorine compounds, that is when fluorine is reacting with other elements, the compounds that we are getting, they are fluorine compounds. They are utilized as a part of toothpaste, drinking water supplies, because fluoride compounds, fluoride means F minus will be present, they react with teeth enamel and counteract tooth rotting. Next element, chlorine, it is utilized for bleaching reaction because it has bleaching capacity in the metallurgy of gold and platinum and in the arrangement of natural halogen compounds. Chlorine is also utilized as a part of cleansing the drinking water, that is for purification purpose. Then iodine, it can kill the germs on the skin without harming the skin. So that is why it can be used as antiseptic. Fine. Now see related question, which of the following is antiseptic? Here we have all the four halogen. So here as it is mentioned, that is iodine. It cannot harm our skin, but it can kill germs. So option 3 will be correct. So you have heard tincture of iodine or iodine tincture. This is actually the name of the antiseptic. Sometimes it is also called weak iodine solution. So it can be asked that what is the composition of tincture of iodine. So that is why I have given this information. 2 to 7% elemental iodine is present in this solution. That means very low concentration. Along with, there is also presence of Ki or NaI. So you also need the iodide salt dissolved in a mixture of ethanol and water. So this is the composition of this antiseptic, which is called iodine tincture or tincture of iodine. Fine. Now we will see how the halogens react with hydrogen, that is their hydride. They all react with hydrogen to form hydrogen halide, general formula is HX. But affinity for hydrogen, that is the tendency to form compound with hydrogen, that will decrease from F to I. That means if we look at these reactions, that is when we are preparing all these hydrogen halide, just look at the condition. When it is fluorine, it will be most, that is its affinity towards hydrogen will be maximum. So that is why in dark also reaction is possible. But when you are moving from F to Cl, now you have to provide more energy compared to fluorine. So that is why now sunlight is required. Next, when you are moving from chlorine to bromine, further affinity towards hydrogen is decreased. So now you have to provide heat. That means higher energy required. And at last, when you have reached iodine, now affinity is minimum. So Not just heat is enough, you also have to provide catalyst. Then only HI can be produced. So this table is actually, from this table it is clear that affinity towards hydrogen decreases as we are moving down the group. And hydrogen halides, when they dissolve in water, because they are gaseous in nature, only HF is liquid, others are gaseous in nature. So when they dissolve in water, then the solution that we get, that is actually the hydrohalic acid. So the HCl solution that you see in the laboratory, that is basically gaseous HCl that is dissolved in water. It is not that HCl is directly liquid. No, that is not the case. Now here we have some properties: melting point in Kelvin, boiling point in Kelvin, then bond length of hydrogen and X in picometer unit, Delitzsch dissociation, that means enthalpy of dissociation of this bond. That is, if you are breaking the HX bond, the enthalpy change, that value is given, and pK value, that is negative logarithm of H plus concentration. So first, if you look at the MP and BP, melting point, boiling point, you can see that normally what we expect as we move down the group, both MP and BP increases because of increasing molar mass, van der Waals interaction increases. But here, as you can see, when you are moving from HF to HCl, our normal expectation is melting point should increase. But here, see, it is 190, but it is 159. That means it is lesser value. Then HBr is also lesser, but HI is high. Because the other factor, that is increase in molar mass, that factor is now winning over it. So melting point is high because as we have already said that fluorine, the first element, it behaves differently, it forms hydrogen bond, but hydrogen bond is not present in case of other hydrogen halides. So that is why here melting point is higher compared to the expected value. And same also for boiling point, from 293 now it is decreased, and even the boiling point of HBr and HI also lesser than HF. Okay. Then bond length, see, there is gradual increase as you are moving down the group, and it is expected because just see H and X. So when it is F, the size is very small. When it is Cl, the size, it is gradually increasing. So when size is increasing, that means the distance between H and X, that is also increasing. So that is the reason for HI maximum bond length for HX. Now, as here bond length is maximum, that means you can easily break HI bond. To break this bond, it is not very difficult. Why? Because bond length is very high. You can easily break it. So that is the reason that Delitzsch dissociation value, just see, this value is minimum and maximum is for HF, because here bond distance between H and F, it is very small. So to break this bond, it is not so easy. Okay. So that is why this type of order. And then pKa. Now pKa, we know that as pKa is basically, sorry, it is pH that I have written here, that is negative logarithm of H plus. But pKa is negative logarithm of Ka. Now what is Ka? It is a dissociation constant of the acid. That means Hx, if it is behaving as acid, it will be dissociated like this. Now here X minus is the conjugate base. When X minus is very stable, what happens? The equilibrium will be easily shifted from left hand side to right hand side. And easily shifted means what? The concentration of H plus will increase. That means acidity will be high. So when H plus is increased, then pH will be decreased, because pH and H plus, these two are inversely related. And pH in decrease means acidity is increased. So when conjugate base is very stable, then it will be shifted towards this. This is one explanation. Another explanation is, if you can easily break this bond, obviously now you can easily generate H plus. So this factor is important here. So Ka is basically H plus concentration, X minus concentration divided by undissociated HX concentration. So Ka value high means what? Now the amount of H plus is high. So when H plus increases, Ka also increases, and pKa, as it is having negative sign, so it decreases. So Ka and pKa, these two are inversely related. That means when acidity is very high, pKa is very low. Now look at the value. pKa is minimum here. That means here acidity is maximum. So the acidity order is maximum acidic HI, then HBr, then HCl, then HF. At a first glance, it seems that HF should be most acidic, because if you apply this logic that here conjugate base, that is F minus, it is more stable because it can uh, stabilize the negative charge over. But here other factor is also operating, which is you can easily break the bond between H and I. So you can easily generate H plus, unlike HF. So that factor is winning over here, and that is the reason maximum acidic is HI, not HF. So now we have this table is very important. See, here HI, then HBr, then HCl, then HF. And this is true for acidic strength, for reducing character also, and for bond length. So when questions will be asked regarding the acidic strength order, you have to follow this order. When question is asked related to reducing character, that means how easily it can generate H. And from HI you can easily get H. That is why its reducing character is maximum. Okay. And also bond length for HI is maximum. So for these three factors, this is the order, same order. And for this right hand side, thermal stability, then dipole moment, bond strength, not bond length. Be careful, it is bond strength. When bond length is very high, bond strength will be low, and stability. So for these four factors, this is the order. Now HF is at the highest extreme. So maximum thermally stable is HF, because bond dissociation enthalpy is very high. You cannot break HF bond easily. So that is why it is thermally stable. Similarly, dipole moment is also high. Now dipole moment, how we understand it? If X is higher, is the electronegativity difference between H and X. Higher will be the polarity difference, and magnetic moment will also be, dipole moment will also be very high. So maximum electronegative is fluorine. So that is why in case of HF, electronegativity difference between H and halogen is maximum. So dipole moment is maximum for HF. And bond strength, it is also maximum, which is clear from this del dissociation, del H dissociation value, because 574, that means very high energy we have to provide. So it means bond strength is very high, and stability, in general stability, that is also high. So remember this last table, this is one order and this is just the reverse order. Okay, and the corresponding properties for which these orders we have to follow, that are also given. So is there any doubt? Any part you want me to repeat? Reaction with oxygen. Halogen do not react directly with oxygen. Fine. But we can make binary oxygen halogen compound. Binary means compound of two elements, oxygen and halogen, by reaction with halogens with some oxygen containing compounds. So direct, if you just add AFC, that is all the diatomic halogens, F2Cl2 and oxygen, there will be no reaction. But if you are taking some oxygen containing compounds, then we can generate their oxide. They can form different types of oxides with oxygen, but most of them are unstable. Now, for fluorine, these two compounds are possible, O2F2, O2F2. For chlorine, now the variety is comparatively high. For bromine and iodine also, see, these are the types that are possible. Oxygen compounds with Cl, Br, iodine, they are called oxide, because here oxygen is more electronegative than Cl, Br, I. So that is why it is called oxide, because oxygen is carrying the negative charge. If oxygen is not carrying negative charge, we cannot say oxide. So that is the reason when you are considering oxygen fluorine compounds, now you cannot call them oxide. So fluorine compounds with oxygen, they are called fluoride, not oxide of fluorine. It is fluoride of oxygen. Try to understand the difference. As oxygen is less electronegative than fluorine, so fluorine will always carry the negative charge and oxygen will carry the positive charge. So we cannot say it oxide. It is not oxide of fluorine. That is wrong. It is fluoride of oxygen. This is the correct way to name this compound. Okay. Now, the first type that we'll see here, that is the compound between oxygen and fluorine. These are the two types that are possible. But among these, OF2 is more stable compared to O2F2 and thermally stable at 298 Kelvin. Both are strong fluorinating and oxidizing agent. That means these two compounds, they are very strong oxidizing agent as well as fluorinating agent. That means by using these compounds, you can add fluorine to other compounds. O2F2 can oxidize Pu to PuF6, and the reaction is used in removing plutonium in the form of PuF6. So see here O2F2, it is acting as fluorinating agent because it is supplying fluorine towards plutonium. It is also acting as oxidizing agent because here Pu is 0, but here it is +6. So from 0 to +6, it is loss of electrons, so it is oxidation. So here it is acting as fluorinating agent and as well as oxidizing agent. And this is also important application of this compound, that this is radioactive actually. So from nuclear fuel, plutonium, if it is required to remove, then we can use this equation because here PuF6 is formed. So Pu can be removed in the form of its fluoride, which is PuF6. So this is oxygen of fluoride. Next we will see oxygen of fluoride, that is chlorine, bromine and argon. So for the next three elements, they can form oxide. Now you can call oxide because oxygen is more electronegative. And oxidation state, these are the variations, that is +1 to +7. All these are possible, but that is not possible in case of fluorine because in case of fluorine only one oxidation state is there. These variation you can get only for the other three elements, not for fluorine. Here we have some examples of chlorine oxide. This is Cl2O. This is ClO2. Okay, see the difference. Here chlorine is having oxidation state, it will be +1 because oxygen is carrying -2. But when it is ClO2, now it is basically +4 because for each oxygen it will be -2. So to balance it, it will be +4. This is Cl2O4. So here two chlorine, their environment not same. If you consider this chlorine, here how many bonds are there? 1, 2, 3, 4, 5, 6, 7. So it will be +7, but this chlorine, it will be only +1. Okay, so two chlorine, not same oxidation state. Next we have Cl2O7. Now both the chlorine are in same environment. So both are 1, 2, 3, 4, 5, 6, 7. That means +7 oxidation state. And this one is Cl2O6. Here also both the chlorine are not having same chemical environment. Here we have total 5 bonds. It will be +5, but this is +7. So these are the different variations for chlorine oxide. They are highly reactive oxidizing agent and so reactive that there is a chance of explosion also. When it reacts with H2O, that is Cl2O7, you are getting this acid, and this is very acidic, perchloric acid, HClO. Now here see Cl2O7, oxidation state of chlorine is very high. So when oxidation state is very high, then the corresponding acid that you are getting by reaction with water. So the corresponding acid is here HClO4. So the corresponding acid, that will be very acidic. And here, as it is acidic oxide, it can react with base and it is generating the salt. See, this is the corresponding salt, HClO4. Just replace H with Na, it will be NaClO4, sodium chloride. ClO2, it is used as bleaching agent for paper pulp and textile and in water treatment. So this is the application of this oxide. Then chlorine 1 oxide, that is the first molecule in the picture. It is far less acidic when you are comparing with Cl2O7, because here oxidation state is +1, here oxidation state is +7. It is true that both of them are acidic in nature, but which one is more acidic? It is Cl2O7, because it is generating this HClO4 acid. But when you are treating Cl2O with water, you are getting HOCl. So HOCl, if we compare acidity, HClO4 is much higher acid, having higher acidity than HOCl. So as it is less acidic, that is the reason. Okay, any doubt? Reaction with oxygen for the next element, which is bromine. So these are the variations that are possible. And remember, when we are talking about bromine oxide, they are actually the least stable halogen oxide. And the reason behind it is middle row anomaly. We will come to that point. What is the meaning of middle row anomaly? It exists only at low temperature because their stability is very bad. They are good, powerful oxidizing agent because stability is very low. So they will always, there will be tendency to take part in reaction. So they are very powerful oxidizing agent. Now, why it is middle row anomaly? See, FClBrI. F is from second period, chlorine third period. This is fourth period, iodine. Okay. So in the middle portion, we have bromine. So that is why we are calling it middle row anomaly, because this anomaly, it is only for bromine. It is not that chlorine oxides are maximum stable and iodine oxides are least stable. It is not that. It is the oxides of bromine that are least stable. Even oxides of iodine are more stable than oxides of bromine. But why it is only for bromine, that we have to see. So what is middle row anomaly? First, look at the electronic configuration of bromine. After argon, 4s2, 3d10, 4p5. So valence shell configuration is ns2, np5. But it is from fourth period, so it will be 4s2, 4p5. But remember, we also have 10d electrons. So these 10d electrons, they are comparatively closer towards the nucleus. And that is the reason, suppose if it is nucleus, all these 3d electrons, they are very close. So as a result, what happens? The repulsion with the 5 electrons of 4p, this repulsion is very less. So as a result, what happens? You cannot remove electrons from 4p5 easily, because suppose if the repulsion between 3d electron and 4p electron, it is very high. So if the repulsion is very high, then you can easily remove the electron from p orbital. But if repulsion is less, it is not easy to remove electron. And when it is not easy to remove electron, that means the corresponding oxides will not also be stable. So that is the reason it is much harder to achieve higher oxidation state for bromine. That is all these. Higher means positive oxidation state. So we are not talking about -1. So when it is +1, you have to remove 1 electron from 4p. When it is +4, you are removing 4 electron from 4p. When it is +6, basically this electron also you have to unpair. Then only you can get 7 unpaired electrons and you can remove 6. So here ionization energy values are very high compared to the expected value because of this less repulsion. But if you are thinking why it is not for iodine, because in case of iodine, now it is 5s2 and 4d10, 5p5. Now see, compared to 3d, when you have 4d, it is comparatively more diffuse, and diffuse means it is not closer towards nucleus. So now repulsion between 4d electron and 5p electrons that are comparatively high. So a ionization energy that will not be very high, because when there is much repulsion, you can electrons will try to that is to remove the electron. That process will be very easy. So this is the reason. And the last element, here we have all these types. They are insoluble solid. Now see, when we have the last elements oxide, that is iodine. Iodine obviously have higher atomic mass. So overall molar mass will be very high. So as molar mass is high, now they are solid. Decompose on heating. Diiodine pentoxide, that is I2O5. It is very good oxidizing agent. And it is so good oxidizing agent that it is used, that is application is estimation of carbon monoxide gas. I2O5 oxidation state of iodine is +5, and after reaction CO is oxidized to CO2, oxidation state +2 for carbon, but now it is +4. So from +2 to +4 it is oxidation. And which is the oxidation agent? I2O5 is the oxidizing agent. And iodine itself is changing its oxidation state from +5 to 0 by gaining electron from carbon monoxide. So this is the reaction by which we can estimate carbon monoxide. And remember, this oxide of iodine, it is the anhydride of iodic acid. Because if you look at the structure, hydride means what? When we say that some compound is anhydride of some particular acid, that means if you have taken HiO3, 2 molecules of HiO3, it is actually having formula H2, I2, O6, and when you are removing one water molecule, what will be the formula? Now it is I2O5. So by removing one water molecule, you are getting this. You can also understand it. Just break this and add here H and OH. See, this is basically hydroiodic acid, HiO3. So I2O5, if it is the anhydride of iodic acid, but in case if you cannot remember it, then also no problem. Just take I2O5 and add water to it. Then the corresponding formula that you will be getting, that is actually the combined formula for 2 HiO3. So in this way you can easily remember the corresponding acid for which it is the anhydride. Okay, so is there any doubt? So related to this, which of the following trend correctly represent stability of oxides of halogen? Remember what you have seen in the last slide? Oxides of bromine are least stable. Okay, so according to that logic, which option should be correct? Bromine should be at last. Now option A, also option B, bromine is at the last position. But you can easily cancel out these two options. But you have to choose between A and B. So how to do it? In oxides of halogen, the bonds are mainly covalent in nature. Because oxygen and halogen electronegativity difference is not very high. So that is why they will not form ionic bond, they will form covalent. The bond polarity, however, increases as we move from F to I. So when it is OF bond and when it is OI bond, obviously the electronegativity difference high in this case, because iodine is more electropositive compared to it. So that is why bond polarity will be higher in case of OI compared to OF. So as we are moving from OF to OCl to OBr, polarity is increasing. So from bond polarity logic, iodine oxide should be maximum stable. So this is one factor. Now come to the other factor. Iodine oxygen bond it is stable because of greater polarity of the bond, and while the stability of ClO, it will be because of multiple bond formation. So one factor is bond polarity, but there is another factor which is multiple bond formation. That is double bond formation is possible between Cl and O. But that is the reason you have seen much variation in the oxides of chlorine, but not such variation is possible for iodine, because this type of double bond formation is possible only between chlorine and oxygen because of size matching compared to if you consider iodine, it is very large in size. So double bond formation is not possible. So the stability, reason of stability, when it is chlorine oxide, the reason is multiple bond formation capacity. But when it is iodine oxide, the stability reason is bond polarity maximum. So both are having its own points. But what about bromine? It is just in between chlorine and iodine. So that is why it is lacking both these characteristics. So this is the least stable. But how to choose between I and Cl? And here basically the bond polarity factor, it is overcoming the multiple bond formation factor. So that is the reason oxides of iodine are more stable than chlorine oxides. So option B will be the correct option. First I, then Cl, then Br. Which of the following statements is not true? Among four statements, one statement will be incorrect. Let's find it. All forms monobasic oxyacid, though we have not discussed it yet. But remember, when we will discuss it, it will be clear. Only fluorine can form one oxoacid. That is true. But one oxoacid is always formed. So all can form monobasic oxoacid. That is always true. So this is correct. All are oxidizing in nature. That is, all the halogens are oxidizing in nature. This is also true. All but fluorine show positive oxidation state. But actually this is not correct because the reverse statement is true. All, that is except fluorine, all can show positive oxidation state. But this statement is actually the opposite. But this is not true. Fluorine can show positive oxidation state. It is the most electronegativity. And chlorine has highest electron gain enthalpy that we have already seen. That is, among these four, maximum electron enthalpy, it is for chlorine. After that, we have all. So this statement is also true. So incorrect option is option 3. So that is why this is the correct option. Okay. So is there any doubt? So this is completely different and it will take time. So I will end today's session here. Next day we'll start with reaction with metals and also interhalogens. So regarding all the slides in the whole class, is there any doubt? Should I repeat any part? Okay. So we are ending the session here. Thank you for listening.